Hello, welcome back to the series on engineering mechanics. Myself Jayarajan P. This is class 2 of the series. This class includes the following topics: 1. Laws of mechanics, 2. Scalar and vector quantities, and 3. Equality and equivalence of vectors. So let us start our class. So let us start with the laws of mechanics. The entire structure of mechanics is founded on the following laws. As you can see in the coming classes, we'll be using these laws very extensively in the study of the force systems and also in the study of the state of bodies. So let us start with Newton's first law of motion. As per this law, every particle continues in a state of rest or uniform motion in a straight line unless it is compelled to change that state by the forces imposed on it. Or in other words, Newton's first law directly tells us the effect of an applied unbalanced force on a body. Means this unbalanced force can force a body to move if it is already at rest. And if a body is in motion, uniform motion, or if the body is moving with a uniform velocity, it can cause acceleration or deceleration. Now coming to the Newton's second law of motion, as per this law, a particle of mass m acted upon by an unbalanced force F, it experiences an acceleration A that has the same direction as the force and a magnitude that is directly proportional to the force. Or in other words, Newton's second law of motion helps us to characterize the acceleration experienced by a body when it is subjected to an unbalanced force F. So referring this is simple sketch, here a particle of mass m, it is subjected to an unbalanced force A. And as per Newton's second law, it starts experiencing an acceleration, the direction of the acceleration being exactly the same as the direction of the force, and the magnitude of the force F required to accelerate the particle by an amount A is obtained from the relation F equal to m into A. So now let us go to the Newton's third law of motion. As per this law, the mutual forces of action and reaction between two particles are equal, opposite, and collinear. To explain this law, as you can see that two particles are shown, particle A and B, and as you can see that they have got a common point of contact. So here the contact is subjected to two forces. One is nothing but that what we call as the force of A on B. Okay, this is represented by this arrow, and then there is another force which is nothing but the force of B on A. And remember that as per this rule, both these forces are equal and they are opposite to each other and they are also collinear. And this third law of motion is very much helpful to identify the various forces at the points of contacts, which we will see in the coming classes. Now the fourth law, that is the Newton's law of gravitational attraction. As per this law, the gravitational force of attraction between any two particles is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. So mathematically, we can say that this force F can be written as F equal to G into m1 m2 by r square. So the various symbols in this formulae are being given here. As you can see that m1 and m2 are the masses of the two particles and r is the distance between them, and F is nothing but the so-called gravitational force of attraction. Okay, so here please remember that there is a constant of proportionality, that is capital G, that is known as the universal constant of gravitation, and this is obtained as G equal to 66.73 into 10 raised to minus 12 meter cube by kg second square. So please remember that while Newton's first and second laws are very much used in dynamics, we use Newton's third law, Newton's fourth law, extensively in the statics. Then next one is the fifth law, that's a parallelogram law. So as per parallelogram law, if two vectors can be represented in magnitude and direction by the adjacent sides of a parallelogram, both pointing away from the common vertex, then their resultant is represented in magnitude and direction by the diagonal of the parallelogram passing through the same common vertex and in the same sense as the two vectors. So look here. So from the above statement, it is very clear that the parallelogram law is used to find the resultant of any two forces. So how this is achieved is very simple. Suppose as referring this sketch, we want to obtain the resultant of any two vectors f1 and f2, okay, which are acting on a body. So what is done as per this law is we construct a parallelogram, okay, with f1 and f2 being the adjacent sides of the parallelogram. Look here, this is the so-called common vertex, and as you can see that f1 is pointing away from this common vertex, and similarly f2 is also pointing away from the common vertex. So what we do is that we construct a parallelogram, okay, with f1 and f2 being the adjacent sides. Now as per this law, right, the magnitude and direction of the resultant of f1 and f2 is represented by the diagonal of the parallelogram as shown here. This is the diagonal of the parallelogram, and this diagonal need to pass through the same common vertex, and it has the same sense as the two vectors. Now the problem is, don't get confused with the direction and the sense. For example, you can say that as far as f1 is concerned, its sense is away from the common vertex. f2 again away from the common vertex. Similarly, the sense of fr is also away from the common vertex. So referring this parallelogram, we can say that vector fr, that is, this is the resultant of f1 and f2, vector fr can be written as vector f1 plus vector f2. Okay, so now let me take you to the other rule, that's a triangle law. And this triangle law can be considered as a special case of a parallelogram law, right? So here what is done is that, so the triangle law is explained, okay, in a very simple fashion using this sketch. So here, look here. So A is one vector, B is another vector. So sketch tells you how to obtain the resultant of the vectors A and B using the triangle rule. So it is very simple. What we do is that we complete two sides of the triangle using vectors A and B, and make sure that vector A is connected to vector B in a tail to head fashion. Now please remember that as far as vector A is concerned, this is the head of the vector, this is the tail of the vector, right? And vector B is concerned, this is the head, this is the tail. Or in other words, we can say that the head of B is connected to the tail of vector A. Now if the two sides are obtained using vectors A and B, then the resultant can be represented in magnitude and direction by the third side. Okay, so wherein you can say that here A and B are the two sides of the triangle, and their resultant is represented by the third side. That is, vector R is vector A plus vector B. Okay, so now referring this sketch, let me just make the statement once again. So the triangle law is a special case of the parallelogram law where one vector is added to another vector in a head to tail fashion. This is what I was explaining. That is, head of first vector is connected. Okay, so this is, look here. So in a head to tail fashion. Okay, so this is the head of vector A that is connected to the tail of vector B. So that is why we say that the connection of the two vectors should be in a head to tail fashion. Now the resultant vector, it extends from, this is my resultant vector, it extends from the tail of the first vector, that is from this point, to the head of the second vector, that is to this point. Okay. Now, applying this triangle law, we can directly use the trigonometry and obtain the magnitude of the resultant force as well as the direction. Okay, so to obtain the magnitude, we can use the law of cosines, and to obtain the direction, we can use the law of sines. So this simple sketch tells you, using the trigonometry and the so-called triangle law, how you can obtain the magnitude of the resultant. Let us say that this is our C is the magnitude of vector R. So how to obtain C? You know A and B, that is the magnitude of vectors A and B, and obviously you know their directions. That means you can easily obtain the included angle C. So knowing A, B and the included angle small c, you can obtain the magnitude of the resultant R as, that is C equal to square root of A square plus B square minus 2AB cos C. Remember, you know the length of two sides A and B, and also you know the included angle C between the two sides. Now, how do we obtain A or B, which determines the direction of vector R? This is simply done using the sine law. Now, referring to the same triangle, we can say that the sine law can be stated as A by sine A is equal to B by sine B is equal to C by sine C. Now, remember that in this sketch, we know C, which is calculated, and we know the included angle sine C. That means using A by sine A is equal to B by sine B equal to C by sine C, we can easily calculate the included angles A and B as well. Okay. So please remember, in the triangle law, we apply the principles of the trigonometry. That means we use sine law and cosine law to determine the magnitude and direction of the resultant force. Now, Polygon law. So in the earlier discussion, that is, we have used the parallelogram law or the triangle law to add two vectors, strictly only two vectors. So in practice, you may find many instances where more than two vectors need to be added. So polygon law can be effectively used to find out the resultant of more than two vectors. Okay, so this is what is written here. The polygon law of vector addition states that if a number of vectors can be represented in magnitude and direction by the sides of a polygon taken in the same order, then their resultant is represented in magnitude and direction by the closing side of the polygon taken in the opposite order. To demonstrate this statement, I have made a very simple sketch. Look here, we have a particle O, okay, right, that is subjected to, how many forces? A vector A, we have got four forces, 1, 2, 3 forces, 3 and 4 forces, and these forces are identified as vector A, vector B, vector C and vector D. Now we would like to find out what will be the resultant of the forces identified by vectors A, B, C and D. And here I have marked the resultant R. So now the question is, how do we obtain the magnitude of the resultant as well as its direction using the polygon law? It is very simple. What we do is that we construct a polygon. Okay, we construct a polygon, right, with each side of the polygon being represented by the various forces. For example, here as you can see that we have constructed the four sides, right, such that the magnitude or the length of each side represent the magnitude of the corresponding forces, and remember that their orientation or the angle of inclination of these various sides will be exactly the same as the vectors represented by that side. Okay, so now we have the four sides, okay, of the polygon being represented by the four vectors A, B, C and D. Now as per this law, we know that the resultant of these four forces can be represented by the fifth side, that means this side. So the polygon law do not require any kind of a derivation. It is very simple. If any polygon can be split up into a number of triangles, for example, as you can see, so this particular polygon, it is split into three triangles. So the first triangle tells us that vector has got the two sides, vector A and vector B. It does mean that the diagonal is represented by vector A plus vector B. Now let us apply the triangle rule once again to the second triangle. We find that the third side is represented by vector A plus vector B plus vector C. Now again applying the triangle law, we'll find that the resultant force is represented by vector A plus vector B plus vector C plus vector D. Because a polygon consists of a number of triangles, so the polygon law is nothing but a combination of the application of the triangle law to each and every triangle of the polygon. Okay, so that's all about the 7 laws that we'll use occasionally in mechanics. Now let me take you to the very important topic, that's the scalar and vector quantities. Obviously, I presume each one of the students know the difference between them. In spite of that, I made a very simple statement. The quantities that have only magnitude are called scalar quantities. So to specify a scalar quantity, you require only the magnitude. So the example of the scalar quantities are the temperature, work, speed, mass, density, etc. On the other hand, we have the quantities that have both the magnitude and the direction, and which need to be added according to the parallelogram law. And these quantities are vector quantities. So this means that to specify a vector quantity, you need to specify both the magnitude as well as the direction. An example of these vector quantities are the force, displacement, velocity, acceleration, etc. Now remember that a vector is shown graphically. It is shown graphically by an arrow. The length of the arrow represents the magnitude of the vector, because we need to specify the magnitude number 1, that is the length of the arrow is equal to the magnitude of the vector, and the angle between the vector and the fixed axis, it defines the direction. Okay, and remember that the head of the arrow indicates the sense of direction. So we have direction and sense of direction. For example, look here. I have shown a very simple force P which is acting on a point A of the body. Now obviously we know that P is a force vector. We need to define or specify the magnitude. Here I have specified the magnitude P equal to 40 Newton. That is, the length of this arrow should be 40 units. Now to define the direction, I need to specify the angle which this P, the force P, makes with the reference axis. In this diagram, it is specified as 20 degrees. Now I need to specify whether this force is acting towards the object or away from the object. That means I need to specify the sense of direction. And here the sense of direction is obviously presented by the head of the arrow, which indicates that the force P is acting away from the point A or away from the object. Okay. So now let us discuss an important concept, that is the equality and equivalence of vectors. So the question is, when we have a set of vectors, when do we say that all these vectors are equal? Or when do we say that all these vectors are equivalent? So the subsequent discussions makes it very clear the terms equality and equivalence. So now let us start. Two vectors are equal if they have the same dimensions, magnitude, and direction. Okay. So now to explain that, so they need to have the same dimensions. Remember, magnitude and direction. So now, what to explain this term equal? Okay, the term equal. What I considered is I have considered the velocity vectors associated with the 3 particles. Here I have a particle, okay, and its velocity is indicated by vector v1. I have a second particle here, and its velocity vector is indicated by v2. And I have got a third particle also, whose velocity is represented by the vector v3. Now remember, number 1, all these are velocity vectors. That means all these vectors v1, v2 and v3, they have the same dimensions. So means you cannot compare a force vector with a displacement vector. You cannot compare for example, an acceleration vector with a displacement vector. So the vectors to be compared need to have the same dimensions. So in this case, they satisfy all our the first criteria. they are all velocity vectors. Accordingly, they have the same dimensions. And here, as you can see, that the length of arrow is each of these vectors have the same length. That means they have the same magnitude. They have the same magnitude. And here again, you can see that the velocity vectors are parallel to each other. What does it mean? It does mean that the vectors v1, v2, and v3, which represent the velocity of the three particles, these are the equal vectors. Okay, they are the equal vectors. Now, though these velocity vectors have different lines of action, they are equal. Remember that v1, v2, and v3, they are having different lines of action as is demonstrated in the sketch. In spite of that, they are equal because they satisfy the basic three criteria. That means they have the same dimensions, same magnitude, and same direction. They can have different lines of action. Okay, so here is shown the normal, the reference axis xyz, and here it represents equal velocity vectors, right? Now that is all about the vector. So remember, two or more vectors are equal if they have the same dimensions, magnitude, and direction, right? Now let me explain, when do we say that the vectors are equivalent? Now, two vectors are equivalent in a certain capacity. This is very important. So we always specify the term equivalence in a certain capacity. If each produces the very same effect, so the equivalence is measured directly in terms of the effect each of this vector produce in that capacity. Okay, now let us refer the same sketch. Suppose we are considering the change in elevation of the three particles. Remember, this is the position where my particle 1 is initially, this is where my particle 2 is, this is where my particle 3 is. So I want to study what would be the change in elevation of the three particles. Okay, what will be the change in elevation of the particles, okay, in a given time. Now look here, we know that v1, v2, and v3, they are the same. They are equal in magnitude. What does it mean? It does mean that in a particular period of time, okay, the change in elevation of all these three particles will be the same. Okay, or in other words, suppose that we are considering other certain capacity. That means we want to calculate what will be the distance traveled by the particles. Obviously, you know that as v1 equal to v2 equal to v3, the distance part covered by each of these particles in a given time span will also be the same. What does it mean? It does mean that considering the change of elevation of the particles in a given time frame, or the distance traveled by the particles in a given time frame, all the three vectors v1, v2, and v3 are equivalent because they produce the same effect. That means if you consider the change of elevation, they produce the same change of elevation in a given time frame. If you consider the distance traveled by the particles, yes, they travel by the same distance in a given time frame. This means considering the certain capacity as the change of elevation or the distance traveled, v1, v2, and v3 are equivalent. So equivalence is always measured in a certain capacity, and this is measured in terms of the effect each of these vector produce. That is very important. Now referring the same sketch, now look here, we know that the starting position of vector the particle for the particle 1 is here, the starting position of particle 2 is here, the starting position of particle 3 is here. Now let us find out what will be the so-called absolute elevation of these particles in a given time. So do you think that in a given time frame the absolute elevation of the three particles will be the same? No, because each of these particles have got different starting point. It does mean if we consider the absolute height of the particles above the xy plane, these vectors will not be equivalent despite their equality. Okay, so means that can find that all the particles after a particular time frame, if you calculate the absolute elevation of the three particles above the xy plane, you will find that all these elevations will be different. It does mean if we consider the absolute elevation as a parameter or the so-called capacity, the absolute elevation, in terms of the absolute elevation, V1, V2 and V3, they are not equivalent because they produce different elevations in a given time frame. So what does it mean? It does mean that a set of vectors can be equivalent or non-equivalent. Everything depends upon the so-called effect we are measuring, because referring this sketch, we have seen that considering the change in elevation and considering the distance traveled by the three particles, V1, V2 and V3 are all equivalent vectors. But considering the absolute elevation of these particles 1, 2, 3 above the xy plane, these are not equivalent. So what does this mean? This means that the equal vectors need not always be equivalent, because we have already stated in our earlier discussion v1 v2 or v3 are equal vectors, but we find that when we measure the absolute elevation they are not equivalent. So with this we come to a conclusion that the equal vectors need not always be equivalent. It depends entirely on the situation considered, or it depends upon exactly what effect we are interested in. So it shall also be noted that the vectors that are not equal may still be equivalent in some capacity. This will be demonstrated. This is a good statement. Okay, will be demonstrated in the next sketch. Look here. Here is a simple beam. Normally we call this such a beam as a cantilever beam with a fixed support at A, and as you can see that this beam is subjected to forces F1 and F2. Now we know that both F1 and F2, they are the forces, so they have the same dimensions. They are parallel to each other, but unfortunately what happens is that here the magnitude of F1 is 25 kilonewton, that of F2 is only 10 kilonewton. It does mean that if you follow the basic definition of the equality, F1 and F2 are not equal vectors. They are not equal. F1 and F2 are not equal because they have different magnitudes. Now let us start analyzing from the consideration of the turning effect each of these force F1 and F2 produces, whether they are equivalent or not. So the effect that we are studying for the equivalence is the turning effect produced by the force. Obviously, we know that the turning effect produced by F1 at the point A is nothing but is the moment of F1 about A, which is 25 multiplied by 2, that is 50 kilonewton meter. Now, what will be the turning effect produced by F2 about the point A? It is nothing but 10, that is the magnitude of the force multiplied by the distance, that is 2 plus 3, 5, that is 50 kilonewton meter. What does it mean? It does mean that though F1 and F2 are unequal vectors, they produce the same turning effect about the point A, which means that in this case, though the vectors are not equal, they are still equivalent as far as the turning effect they produce about the point A is concerned. Okay, so to summarize our discussion on equal vectors and equivalence, it can be stated that the equality of two vectors, it is determined by the vectors themselves. It is determined by the vectors themselves. That is very important. Whereas the equivalence between two vectors, it is determined by the task involving the vectors. By the term task, I mean what kind of the effect we are going to study in order to check the equivalence of the two vectors. Okay, so I think that's all about today's class. We'll come with the interesting topics in the next class. So thanks a lot and have a nice day.